Whoa, dude, today we're talking about some waves. Not these kind of waves, though. We're talking about more common waves. You know, like the waves all around us. The waves that you use for your cell phone, internet, sound waves, everything else. We're going to talk a little bit about the ocean waves, but it's not just about that. We're going to be learning all the common characteristics, the units, how we can measure the speed of waves, how we can measure how long it's going to take for the next wave, the frequency. All these terms you guys are going to get used to because this is what we are going to be talking about for the next few weeks. First thing you need to know about is the period for the wave. It's the time to complete one vibration or one wave. It's the time for the wave to go an entire cycle. Now we don't use P because P is used for power, momentum, and that's already confusing. So instead we use a capital T, which makes sense because period is measuring the time for the wave. And the units for that would be in seconds. So we would say that a wave occurs every 4 seconds would be the period of the wave. Next is frequency. Frequency and period go hand in hand. Frequency is the inverse of period. All right? So frequency is the number of waves per second, or the number of vibrations per second. For this, we use hertz, named after the scientist, and that's a hertz equal to a wave per second, and it's shortened as capital HZ. So 300 vibrations per second is the same thing as saying 300 hertz. If I said 10 waves crash on the beach in a time of 3 seconds, you could say the frequency of those waves is 3.3 hertz. And we're going to be learning more about that equation. Like I said, frequency is the inverse of period, or period is the inverse of frequency. So T, which again stands for period, is equal to 1 over F, which is 1 over the frequency, or frequency is equal to 1 over the period. So if you know the period, you know frequency. If you know frequency, you know the period, you just have to take 1 divided by that number. An example. Here we're on the beach. Whoa, surf's up, dude. And you count 10 waves crashing onto the shoreline in 15 seconds. What's the frequency and period of the water waves? Well, if you find one, the other one's pretty easy. So frequency is the number of waves divided by the time. So we would take 10 waves divided by the 15 seconds. You do the math and you get 0.67 hertz is the frequency. All right. Well, what if you wanted to tell your friend how much time will pass before the next wave hits, so that you could, I don't know, surf the wave? You would say, well, if it's 0.67 hertz, if I take 1 divided by 0.67, we could find the period, and that period is 1.5 seconds. So every 1.5 seconds, you should have a wave coming through. Now, there's different parts of the wave. All right, we've already talked about wavelength. What the wavelength is the distance between any two similar successive points. What that means is that you could find the wavelength from crest to crest, because those are two similar successive points, trough to trough, or you could go from the equilibrium position, which is this line through the middle, from the equilibrium position as you go up to the crest, all the way to the equilibrium position as you're traveling up again. So again, the wavelength would be from this equilibrium position, we have a half a wave there, another half there, and we have 1 full wave coming back up. You have the amplitude. Amplitude as an amp energy drink, or the amp that you use for your guitar. That's going to tell how loud or how big the wave is, and that's from your equilibrium position, the center point, up to the crest, or the equilibrium position down to the trough is the amplitude. If I tell you that the distance from the trough to the crest is 2 meters, you would take that number and you would cut it in half so that you just have the amplitude from the equilibrium position to the crest, and that would give you a 1 meter amplitude. Right? Like I said, the crest is the top of the wave. The trough, kind of like what animals eat out of, would be the bottom of the wave. You look here and check out how many wavelengths are pictured. In this blue section, if I start from the equilibrium position, I go up, I have a trough, go down through go up through the crest, down through the trough, you have one wave. And this yellow section, or not the yellow section, the red section, if I start from the crest and I go to the trough, that's only half of a wave. You want one full crest, one full trough in order to make a complete wave. And the blue section here, we start from a crest, start from a trough, we go to the crest, it's a half a wave, we go down, have another trough, so that would be from trough to trough, one wave, and then we go back up to the crest, so that's 1 1/2 waves. And then this part, we have the equilibrium position and half of a trough, which would be a quarter of a wave. This symbol here, it looks like an upside down Y, we're going to discuss shortly, but that's a Greek symbol, lambda, and it stands for wavelength. When we're talking about wave motion, many people think that the waves are transporting the particles. Particles are moving all throughout. Really, it's transporting energy. The particles just vibrate back and forth or up and down, much like a bobber floating on top of water. The bobber isn't going all the way down to the bottom and all the way back up. The bobber is going to oscillate up and down as the water passes by. Right, but it still stays in that same horizontal location. It's not going to go left and right. It just goes up and down, much like the wave particles. Wave speed. This is our our third equation. Wave speed is equal to the wavelength times frequency. The equation is right here. Velocity, v, wave speed, is equal to this Greek symbol lambda, which represents wavelength, times f, or frequency. From this, you can figure out that the wavelength is equal to wave speed divided by frequency, or frequency is equal to wave speed divided by wavelength. Here's an example of how we can use that to figure out the period of the wave and the wavelength. So you have a 900 megahertz cordless phone. They travel at the speed of 3 times 10 to the 8th meters per second, which is the speed of light, or the speed of electromagnetic waves in a vacuum. And it wants you to find the period and the wavelength of this cordless phone. To do this, you guys can try it on your own, but make sure you turn 900 megahertz to hertz. And to find that period, remember it's 1 divided by frequency. And then to find the wavelength, you would do wave speed divided by frequency. Frequency has to be in hertz. And here's how to get that solution after you guys tried it on your own. There are two types of waves that we're going to talk about. The first type of wave is a transverse wave. Wave particles vibrate perpendicular to the direction of motion. So what happens is the wave particles are going to move up and down, but the wave motion is going to be horizontal. So we say that the wave motion is perpendicular to the direction of travel, right? Water waves, waves on a rope, our electromagnetic waves, they're all going to travel as transverse waves. When we represent waves, most of the time you'll see us representing them as transverse waves. The other type is longitudinal waves. Longitudinal waves is a less common type of wave. Really, sound is the major one that travels like this. And what happens is that the wave particles are going to move back and forth, and the wave direction, or the direction of travel, is also going to be along the same line. So we say that the particles vibrate along the direction of the wave. Like I said, sound waves travel like this. You could think of other examples like waiting in line for a roller coaster ride, or waiting in traffic are longitudinal wave type examples. You have compression and then expansion. Compression is equal to the crest. Expansion is equal to the trough. Longitudinal waves, they are stationary, and what happens is if I were to hit this tuning fork, you would have these molecules move back and forth. Here in the compression, again, you would have maximum pressure, and here where there's not compression, or what we call the rarefaction, you would have a gap, and this would be like the trough. There's other types of waves. You have mechanical waves, which require a medium to travel through, kind of like ocean waves. You need water for it to travel. And then the median is the substance that a wave travels through. And then you have electromagnetic waves. Electromagnetic waves are your most common waves. They don't require a medium, which is how you can get these waves to travel through space. So satellites use electromagnetic waves. Light, anything that can travel through space, you get. Now, since we can't talk in space, that would mean sound needs a medium and is a mechanical wave. We've discussed this earlier. The speed of light is 3 times 10 to the 8th meters per second, which is equal to 186,000 miles in 1 second. So in 1 second, light can travel around the Earth 7 times. Of all the waves that are out there, we can only see very little. All the way from from violet to red. Ultraviolet is just outside our spectrum, which you guys might know. In the summer, you have the UV rays, and those, well, as you know, get you sunburnt. Okay, they're very high energy. They can penetrate the skin and burn you. And then you have infrared rays, which you have the infrared goggles, which let you see at night because it measures the heat coming off of you. Here you have the electromagnetic spectrum. AM radio waves are our longest waves. They can travel a great distance, followed by the FM radio, the microwave, radar, all these things that we use all the time. Then you get to the visible light, which is very, very small, infrared. After that, you go to the X-rays, which will penetrate your skin, but not the bone, which is how you're able to see broken bones. And lastly, anybody plays Call of Duty and you get the 25 kill streak, you'll know what the last one, your gamma rays, radioactive rays, or your nuclear rays. Those are our most highest energy type of waves. And that is our introduction into waves. I hope you enjoyed it. If you have any questions, please ask your teacher. And surf's up.